Hello and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy, and in this video we'll be discussing continuous probability distributions and their expected values. The previous video developed the fundamentals of discrete random variables. This video will tackle continuous random variables. As we did with discrete random variables, we'll start by defining continuous random variables and their sample spaces. The definition of a random variable hasn't changed from our previous video. It is a variable which takes as its value the outcome of a random event. Here are some examples of random variables, different from the examples in the previous video. Wind speed at Hospital Point on class days, temperature on Warden Field, and height. The definition of a sample space also hasn't changed from our previous video. It is the set of possible outcomes of a random variable. I've capped the sample space of wind speed at 64 knots based on my belief that classes will be cancelled in the event of hurricane force winds. I at least will not be in class if local winds exceed 64 knots. The sample space of temperature on Warden Field is approximately the range of temperatures observed in Annapolis. The sample space of human height, 0.5 meters to 2.75 meters, is approximately the range of adult heights ever observed. In our last video, we defined discrete sample spaces as those that are countable. A continuous sample space is any sample space that is not discrete. A random variable is continuous if its underlying sample space is continuous. We will restrict attention to continuous random variables with sample spaces of the form AB, i.e. the interval of real numbers greater than or equal to A and less than or equal to B. All of the sample spaces listed above are continuous, and therefore all of the random variables listed above are continuous. To each discrete random variable, we associated a probability mass function. To each continuous random variable, we associate two functions, the cumulative distribution function and the probability density function. Unlike the discrete case, the definitions of these functions don't make explicit mention of an underlying random variable. First, we'll define these two special functions, and then we'll explore the relationship between these functions and an underlying random variable. A cumulative distribution function, often abbreviated CDF, is one which satisfies the four properties shown. Its limit as x approaches negative infinity is 0, its limit as x approaches infinity is 1, it is non-decreasing, and it is right continuous. We will restrict our attention to fully continuous CDFs. A cumulative distribution function fully describes the behavior of its underlying random variable. Each cumulative distribution function has an associated probability density function, often abbreviated PDF. The probability density function little f associated to a cumulative distribution function big F is the derivative of big F. The convention is to use a capital letter to denote a CDF and the corresponding lowercase letter to denote the associated PDF. Using the probability density function, we can recover the sample space of a continuous random variable. The sample space is the support of the probability density function, i.e. where it takes non-zero values plus any endpoints of that set. The probability density function has two very important properties outlined in this lemma. First, the probability density function takes only non-negative values. Second, its integral is equal to 1. You should take a stab at proving each of these properties using the definition of the cumulative distribution function. These properties are very similar to the properties of a probability mass function, and indeed the PMF and PDF serve as weighting functions for discrete and continuous random variables respectively. However, it's really super important to note, the PDF little f of x does not tell you the probability that x occurs. As usual, let's give an example. Here is a CDF for wind speed, which I admit I made up for the purposes of this example because the math works out nicely, rather than basing it on any kind of data. We said that the CDF fully describes the behavior of its underlying random variable, so from the CDF, we should be able to determine the PDF and the sample space of the underlying random variable. Pause the video for a few moments to try the problem, and when you are done, unpause it to see the solution. To verify that big F is a CDF, we need to show that it tails off to 0 as x approaches negative infinity, levels off at 1 as x approaches infinity, is non-decreasing, and is right continuous. We can see from the definition of big F that it satisfies the first two properties. We can check that big F of 0 is equal to 0 and big F of 64 is equal to 1, so big F is continuous. To see that big F is non-decreasing, compute the PDF little f, which is everywhere non-negative, so big F is non-decreasing. So we've computed the PDF and verified that it is non-negative. We can also see that the sample space consists of numbers greater than or equal to 0 and less than or equal to 64, since that interval and its endpoints are the region where little f is non-zero. With some admittedly sloppy notation, we see that the PDF indeed integrates to 1. We are now, at long last, ready to say how the CDF relates to probabilities of certain outcomes. The CDF, big F of x, tells us the probability that a random variable takes on a value less than or equal to x. We can also use the CDF to describe the probability that a random variable takes on a particular range of values, i.e. the probability that x is greater than or equal to a and less than or equal to b is f of b minus f of a, which is also the result of integrating the PDF from a to b. Let's use our CDF for wind speed to find the probability of some wind speed events. The probability that the wind speed is not more than 32 knots is f of 32 equals 3/4. The probability that the wind speed is at least 4 but not more than 20 knots is f of 20 minus f of 4 equals 13 out of 32. The probability that the wind speed is exactly 6 knots is the probability that it is between 6 and 6 knots, which is 0. Now we appear to have a problem. There's nothing special about our choice of 6. For any number k, the probability that the wind speed is exactly k knots is 0. On the other hand, the wind speed has to be some number. We could go out to Hospital Point and measure it. Suppose we go out and measure 6 knots. A probability 0 event has occurred. How should we understand this? There are two ways I like to think about it. One is that measurement error means that when we measure exactly 6 knots, we're really determining that the wind speed is close to 6 knots, and close to 6 knots is a positive probability event. As we make close a smaller and smaller range around 6, the positive probability assigned to the event close to 6 knots gets smaller and smaller and approaches 0. The other way I like to think about it is by imagining living in a world with some finite number of wind speeds, say 0 and 64 knots. Then wind speed would be a discrete random variable described by some PMF. Then I imagine moving from that world to one with a larger but still finite number of wind speeds, say 0, 32, and 64 knots. Wind speed would still be a discrete random variable described by some PMF, but 0 and 64 would be somewhat less likely, and 32 would be somewhat more likely. Then I move on to the next world with still more possible wind speeds, say 0, 16, 32, 48, and 64 knots, and repeat the process. As I move to each successive world, I get closer and closer to the continuous version described by the CDF big F. We still haven't provided an interpretation of the PDF except to say that little f of x does not describe the probability that x occurs. Rather, the PDF is a weighting function that tells us the relative likelihood of different outcomes. Let's use our PDF for wind speed to calculate some relative likelihoods. A wind speed of 0 knots is twice as likely as a wind speed of 32 knots because little f of 0 is equal to 1 over 32 and little f of 32 is equal to 1 over 64. 0 knots and 32 knots are both probability 0 events, but nevertheless, 0 knots occurs twice as often as 32 knots. The PMF of a discrete random variable also serves to tell us relative likelihoods. It is through this relative likelihood property that both serve as weighting functions. This table shows all the parallels together. Last, but certainly not least, we should define expected value. Expected value is a weighted average, using the probability density function as the weighting function. Expected value really makes sense only for a random variable that takes on numerical values. Let's compute the expected wind speed on Hospital Point. First, distribute. Now, integrate. Evaluate from 0 to 64. A bit of arithmetic, and we see the expected wind speed is 64 over 3 knots. We can also further suspect that I made up the underlying CDF because 64 over 3 knots does seem stronger than typical. Thanks so much for watching this video about continuous probability distributions.